Welcome to the deep dive. You sent us this paper on the compositional generalization of multimodal LLMs for medical imaging, and we're going to take a deep dive into it today.
Yeah, it's really exciting research.
Yeah, super interesting stuff. Buckle up, listeners, because we're going to be exploring the future of AI in healthcare.
It's a fascinating area. We're going to be talking about multimodal large language models, or MLLM.
MLLMs, got it.
Yeah, so these are AI models that can analyze both text and images.
So, kind of like a doctor who can read your chart and look at your x-ray at the same time.
Yeah, exactly. Like a superpowered medical detective.
Yeah, like that.
But there's a catch. These MLLMs, they often struggle when they don't have enough data, especially for rare conditions.
Right, that makes sense.
And that's where this research comes in. It explores how these models can learn from lots of different types of medical images.
Okay, so what if an AI trained on x-rays of broken bones could actually learn something useful from an ultrasound of the heart?
That's exactly the question that these researchers tackled.
Okay, I am hooked. Tell me more. How did they figure this out?
Well, they created this massive data set called MedMat.
MedMat.
Yeah, and it's a collection of 106 medical data sets.
106.
Yeah, covering a huge range of imaging types.
Wow.
We're talking X-rays, MRIs, even microscopic images of cells.
That's a lot of data.
It is. And they didn't just throw all these images together randomly. They very carefully organized this data to see if training an MLLM on a mix of, related data sets could actually improve its performance.
Interesting.
And they actually have a name for this principle. They call it compositional generalization.
Compositional generalization.
Yeah, or CG for short.
CG, I got it.
Yeah.
So how does the CG thing actually work in practice?
Imagine learning to build with Legos.
Okay.
If you know how to build a house and you know how to build a car separately, you can then combine those skills to build a garage, right?
Yeah.
So MLLMs, they can do something very similar with image features. They learn these basic building blocks from different images, and then they can use those blocks to understand new images, ones they've never seen before.
So it's like giving the AI a Lego set of medical knowledge.
Yeah, exactly. That's a great analogy.
Yeah, I like that a lot.
So does the paper give any specific examples of this Lego-like learning in action?
Yeah, I was going to ask that.
Absolutely.
Wait, yeah, me.
Let's say an MLLM is trained on CT scans of lung cancer, to identify cancerous areas.
Okay.
Now, let's say it's also trained on brain scans to diagnose, different brain conditions.
Okay.
They found that this model could then apply its knowledge to understand CT scans of brain cancer, even though it had never actually been specifically trained on that condition.
Wow, that's amazing. So even with limited data on a specific condition, the MLLM can potentially learn from other related images.
Exactly.
This could be revolutionary for diagnosing rare diseases, where data is often scarce.
Absolutely. It means we might be able to diagnose these conditions earlier and more accurately, even if they're incredibly rare.
This MedMat dataset sounds like a real game changer.
It is.
Can you give us a sense of the variety of images it contains? You mentioned microscopic images. Anything else that might surprise our listeners?
Well, aside from, the usual X-rays and MRIs,
Right.
they've got images from endoscopies, which allow doctors to see inside the body.
Ah, interesting.
And fundus photography.
Fundus photography.
Which captures images of the back of your eye. They even have data from optical coherence tomography.
What is that?
It's this specialized technique used to create these super detailed images of the retina.
Oh, wow.
Yeah, it's quite a collection.
That's incredible. And they turned all these different images and labels into a question answering format.
Right.
Why did they do that?
What makes it easier for the MLLM to actually learn. So the model is presented with an image, and then it's asked a question about it, like what type of cell is this, or is there a tumor present? And then the MLLM has to choose the correct answer from a set of options.
Oh, that's cool. So they've shown that these MLMs can learn by combining knowledge from different types of images, right?
Yeah.
But how did they prove that this compositional generalization isn't just a fluke?
Well, that's where their experiments come in.
Okay.
They tested out different scenarios,
Huh?
including using data sets with no overlap in image types or body areas or medical tasks. And what they found was that without that connection, the MLLM's performance really dropped significantly. It's all about the connections.
So it's not just about feeding the MLM a ton of data.
Oh, no.
It's about making sure that the data is actually related in a meaningful way.
Exactly.
This is where that Lego analogy really clicks into place.
Right, exactly. The more relevant building block that model has, the better it can understand and generalize to new situations.
Okay, so more related data leads to better results. But what about those situations where we just don't have a lot of data to work with? Like, with those rare conditions we talked about earlier, did they explore that at all?
They did, and this is where things get really interesting.
Okay.
They found that even with very limited data on a specific task, incorporating CG into the training process helped the model to learn much more quickly and effectively.
So even if there's not a lot of information available about a particular condition, CG can help the MLLM learn from other, related images.
Yeah,
This could be huge for patients with rare diseases.
absolutely. It essentially allows the model to, transfer knowledge from more common conditions to those that are less understood.
Now, we've talked about CG in the context of two related elements, like using X-ray images of the lungs to understand X-ray images of the bones. But did they ever test CG with all three elements, the
Mhm.
image type, the body area, and the medical task coming from totally different data sets?
They did,
Ah,
to make sure that the model wasn't relying on any shared elements between the data sets.
interesting.
And what's remarkable is that CG was still effective in most of those cases.
So even when pulling information from completely different sources, this approach still worked. That's impressive.
It is.
It really shows you how flexible this technique can be.
It highlights the power of this approach. And to be even more thorough, they didn't just test CG on one type of MLLM, they actually tested it on a few different models, each with its own unique design and training methods.
And what did they find? Did CG hold up across the board?
It did, which really suggests that CG isn't just a fluke or a quirk of a particular model.
Right.
It seems to be like a fundamental principle underlying how these multimodal language models learn.
That's a powerful statement. So it's not just about the specific models, but about something much deeper,
Yeah.
something inherent in the way these models process and integrate information from both language and images.
Precisely. And that opens up a whole new world of possibilities for how we train AI models in the future.
Yeah. This is fascinating stuff. We've covered a lot of ground already, but I know there's still more to unpack. What other aspects of this research should we explore? So we were just talking about how the researchers tested compositional generalization on multiple models and it held up across the board.
It did, yeah.
It really seems like CG is this key ingredient in the secret sauce of how these MLLMs learn.
Yeah, it's really a groundbreaking finding.
Yeah.
And it points toward this future where AI can, learn and adapt in ways that we previously thought were impossible.
It's really cool.
It is. But, as with any new technology, there are still, some challenges to overcome.
That makes sense. What are some of the areas where the researchers see a need for, further exploration?
One thing they highlighted was the need to, delve a little deeper into understanding exactly how WCG works.
Right.
While their research, strongly suggests that it's a major factor in MLLM learning.
Yeah.
It might not be the whole story.
Oh.
Even when they intentionally disrupted the conditions for CG, the model still showed some level of generalization.
So there are other factors at play.
Right. That's interesting.
It reminds us that, the world of AI is rarely simple. There's always another layer to uncover.
Yeah, for sure.
Unraveling those hidden layers and understanding, the complex interplay of factors that contribute to an MLLM's ability to generalize. That'll be a key focus for future research.
We've talked a lot about CG involving two elements of that MAT triplet you mentioned earlier.
Right.
Things like using data from X-ray images of the lungs to help understand X-ray images of the bones.
Yeah.
But did the researchers also explore CG with all three elements coming from different data sets?
Yeah, they did. And the results are pretty fascinating.
Okay.
They designed experiments where the image type, the body area, and the medical task all came from completely separate data sets.
Wow.
It's kind of like taking the engine from a car, the wings from a plane, and the propeller from a boat, and seeing if you can build something that flies. That's a great analogy.
And in most cases, the MLLM could make something fly, so to speak.
Mm-hmm.
The fact that CG still worked, even when they pulled the modality from one data set, the anatomical area from another, and the medical task from a third.
Wow.
It really highlights the flexibility and power of this approach.
That's incredible. It's like the MLLM is this master chef,
Yes.
who can just take these random ingredients and whip up a Michelin star dish.
It's a great analogy.
I like that.
It really reinforces that idea that CG is this robust principle that can handle these complex combinations of information.
Now, you mentioned earlier that there are still some challenges to overcome.
Right.
One that comes to mind is, the need for large amounts of data.
Yeah.
We've been talking about this massive MedMat data set.
Right.
But in the real world, we don't always have the luxury of such extensive data sets,
Yeah, that's true.
especially when you're dealing with, rare conditions.
Right.
Did the researchers address this limitation at all?
They did. And their findings in this area are particularly exciting. They conducted experiments to see how CG could help with what they call data-efficient training.
Data efficient training.
Yeah, this is all about making the most of limited data,
Okay.
which is, really crucial for rare diseases where gathering huge data sets can be incredibly difficult.
Absolutely.
So how did CG perform in these data-efficient scenarios?
That's what I was going to ask.
Well, they started with a very small amount of data for a specific task,
Okay.
and they gradually increased it.
Mm-hmm.
What they found was that incorporating CG combinations into the training process allowed the model to learn much more quickly and effectively,
Even with that limited data.
even with limited data on the target task itself.
Yeah, that's huge, especially for those rare conditions we keep talking about. Imagine being able to train an AI model to diagnose a rare disease, even if we only have, a handful of images to work with.
Exactly. It's like, teaching a detective to solve a crime with only a few clues. CG helps the MLLM connect the dots and, make inferences based on its knowledge of, related cases.
We've talked a lot about CG in the context of classification tasks,
Right.
identifying what's in an image.
Mhm.
But the paper also mentions that they tested CG with two different MLLMs capable of object detection.
Yes.
Can you remind us what object detection is and how it differs from classification?
Of course. So classification is like labeling an image.
Oh,
You
okay.
say, this is a picture of a cat, or this X-ray shows pneumonia.
Right.
Detection goes a step further. It not only identifies what's in the image, but it actually draws a box around it,
Oh, okay.
pinpointing the exact location.
So it's not just saying you have a problem.
Right.
It's drawing a circle on the X-ray and saying the problem is right here.
Precisely. It adds this level of precision that's really crucial for a lot of medical applications.
Absolutely.
And the exciting part is that CG works for these detection tasks as well.
Really? So you can use CG to help an MLLM not only identify a condition, but also pinpoint its location within an image.
Yes.
That's powerful stuff.
It is. They tested CG with two specific models that were capable of detection, NextChat and Mini GPT v2.
Okay.
Each model approaches detection in a different way, but both were able to successfully use CG to generalize from detection tasks to classification tasks.
Wait, so training on one type of task actually helped with a completely different task? How is that even possible?
It's all about the connections CG enables.
Okay.
Think back to our Lego analogy.
Right.
Even if you're building a different structure, the basic building blocks and the principles of construction,
They remain the same.
they remain the same. Similarly, the MLLMs can leverage the knowledge they gain from detection tasks to improve their performance on classification tasks,
Interesting.
and vice versa.
That's fascinating. It suggests that CG isn't limited to a single task or a specific type of problem.
Right.
It has this potential to, bridge the gap between different tasks,
Yes.
making MLLMs even more versatile and powerful.
Exactly. This research has opened up this whole new world of possibilities for how we can train and utilize AI, in healthcare and beyond.
This has been an incredible journey so far.
It has.
But before we wrap up, I want to address something that might be on our listeners' mind.
Okay.
We've been talking about all these different models: Alavia, NextChat, Mini GPT v2, Qwen 2VL, Llama 3.2 Vision.
Right.
It might seem like CG is just this, happy accident that happens to work with these particular models.
Yeah.
Is there any reason to believe it's a more general principle?
That's a great question. And it's something that the researchers were, very careful to address. They didn't want their findings to be limited to, just a few specific models.
Right.
Remember, their goal was to investigate CG as this, fundamental learning principle.
Right.
So they intentionally chose models with, a variety of architectures and training approaches to see if CG held up across the board.
And did it?
It did. As we've discussed, CG proved effective across all the models that they tested.
Wow.
This strongly suggests that CG isn't tied to any specific architecture or training method.
Yeah.
It seems to be a more fundamental principle, applicable to a wider range of MLLMs.
That's a huge takeaway. It means that the potential of CG extends far beyond the specific models used in this research.
Yes.
We're talking at a fundamental shift in how we think about AI and its ability to, learn and adapt.
Exactly. This research has really laid the groundwork for a future where AI systems can learn and generalize in ways that, we're only beginning to imagine.
This deep dive has been mind-blowing.
It
We've
has.
explored this groundbreaking research on CG, its potential to revolutionize healthcare, and its implications for the future of AI in general.
It's been a fascinating exploration,
Yeah,
and this is just the beginning. There's so many avenues to explore, so many questions to answer,
right.
and so much potential waiting to be unlocked.
I completely agree. I'm already eager to see where this research leads and what other breakthroughs are on the horizon.
Me too.
Thank you so much for, guiding us through this intricate and exciting world of AI and compositional generalization.
Oh, the pleasure was all mine. I'm always thrilled to, share my passion for AI and to explore the amazing things we could accomplish when we combine, human intelligence with the power of machines.
So we've been on quite the journey exploring this whole concept of compositional generalization and how it's really kind of changing the game for AI in medical imaging.
Yeah, it really is remarkable to see how these AI models can learn from a mix of information, almost like piecing together a puzzle to understand something new.
Exactly. And the implications go way beyond just reading x-rays or MRIs.
Oh, absolutely.
We touched on this a little bit before, but I kind of want to dive a bit deeper. What other fields could be impacted by this kind of AI learning?
Well, I mean, the possibilities are truly vast.
Hmm.
Imagine the impact on personalized education, for example.
Okay.
An AI tutor could draw from this huge library of resources, right? Customizing its teaching style based on how a student learns best. It could even spot patterns in their struggles and adapt its approach, in real time.
It's like having this personal tutor that can tailor, every lesson to your exact needs.
Exactly.
That's incredible. What about like other areas?
Well, robotics is another field that could be completely revolutionized by this. Instead of, being programmed for specific tasks, robots could learn by observing demonstrations of different but, related actions.
Oh, interesting.
This would make them far more adaptable and versatile in, these complex real-world environments.
It's like teaching a robot to cook by showing it how to chop vegetables, stir ingredients, and control the stove. Eventually, it could learn to like prepare a whole meal just by observing those individual actions.
Exactly. It's about, breaking down these complex tasks into smaller, more manageable pieces, and then letting the AI figure out how to combine them in these, new and creative ways.
This kind of AI learning feels much more, I don't know, human-like. It's not just about following instructions, it's about understanding and applying knowledge in different contexts.
That's a key point. We're moving away from AI systems that are, rigid and task-specific towards systems that are more, flexible, adaptable, and capable of independent learning.
This is really exciting stuff. But as with, any powerful technology, we need to consider the potential downsides as well. What are some of the, challenges or limitations that researchers are still working to address?
One key challenge is ensuring that these AI systems are developed and used responsibly, right?
Of course, yeah.
We need to be mindful of potential biases in the data used to train these models and ensure that they are fair and equitable for everyone.
Yeah, absolutely. We don't want AI to perpetuate existing inequalities or create new ones, right? It's important to have, diverse teams working on these technologies and to carefully consider the ethical implications at every stage of development.
Absolutely. And while this research has shown the power of CG, we also need to remember that it's still early days.
Right.
There's much more research to be done to fully understand how these models learn and generalize and to ensure that they are reliable and trustworthy in real-world settings.
So there's a lot of work ahead, but the future looks, incredibly promising. What are some of the key takeaways you hope our listeners will kind of walk away with from this deep dive?
Well, first, I hope they appreciate the incredible potential of AI to transform healthcare and, countless other fields. The ability of these models to learn and adapt is truly remarkable, and we're only just scratching the surface of what's possible.
It's like we've opened this door to this whole new world of like AI possibilities.
Exactly. And second, I hope they understand that this technology is not some distant, science fiction concept. It's happening now, and it's going to have a profound impact on our lives.
Right.
It's important to stay informed, ask questions, and engage in conversations about how we want to shape this future.
That's a great point. AI is not something to be feared or ignored. It's a tool that we can use to create a better future for everyone. But we need to be thoughtful and deliberate about how we develop and deploy it.
Well said. And I think the final takeaway, and perhaps the most important one, is that this research underscores the power of human ingenuity,
Mm.
right? It's scientists, engineers, and researchers who are pushing the boundaries of what's possible, driven by this desire to, solve problems, improve lives, and create a better world.
It's inspiring to see what we can achieve when we combine our creativity and determination with the power of technology.
Absolutely. And as we continue to explore the potential of AI, it's important to remember that it's not just about the algorithms or the code. It's about the people who create these technologies, the people who use them, and the potential they hold to make a positive impact on the world.
That's a beautiful sentiment to end on. Thank you again for joining us on this incredible journey into the world of AI and compositional generalization.
It's been a pleasure.
It's been an eye-opening and thought-provoking conversation, and I hope our listeners are as excited about the future of AI as we are.
The pleasure was all mine. I'm always thrilled to, share my passion for AI and to explore the amazing things we can accomplish when we combine human intelligence with the power of machines.
To our listeners, we hope you enjoyed this deep dive. Remember, the world of AI is constantly evolving, so keep exploring, keep learning, and stay curious. And who knows, maybe one day you'll be the one making the next groundbreaking discovery in the field of artificial intelligence.
And when you do, be sure to send us your research. We'd love to have you back on the deep dive to discuss it.
Until next time, keep diving deep into the fascinating world around us.